Okay, Victor, accelerated Stein variational gradient flow.
Okay, yeah, so thank you very much for the invitation, Stan, and thanks, Shu, for organizing. My name is Viktor Stein. I'm a PhD student from Berlin, and I visited Wuchen last year, and this is the project we've been working on together ever since. So it's called Accelerated Stein Variational Gradient Descent, and as Wuchen mentioned, now that my last name is Stein, it's basically only a matter of time until I worked on something with Stein variational gradient flow. So my talk has these 6 chapters I want to go through a view, and the first 3 are basic stuff you already know. So I'm going to talk about sampling from densities, about Stein variational gradient descent, and about Nesterov's accelerated gradient descent. And then I'm going to explain how we put them together in an interesting way to yield a better algorithm for sampling for densities, namely accelerated Stein variational flow in the space of densities. And I'm also going to explain the type of particle discretization we've used, because this inherits basically the nice ideas and concepts from Stein variational gradient descent, but keeps these accelerated properties as well. And I'm going to close with some numerical examples to hopefully convince you that we've come up with a good method. So as always, please interrupt if there's any questions. So in sampling, our task is to sample from some density pi, which up to a normalization constant will be e to the minus v, where v is some potential. And this is frequently applied for Bayesian inferences and for generative modeling, for example. And there are 2 basic schools of thought, 2 main lines of research, as Krishna pointed out in his talk about SVGD like a month ago, I think. So there are these diffusion-based methods, so Langevin type methods, MCMC methods, they are usually called, and they discretize some diffusion process. dy dt is minus grad of v, the target potential, plus some Brownian motion. And this represents like a Markovian process whose stationary distribution is the distribution v we want to sample from, or the potential v, which defines the distribution we want to sample from. And one can then explicitly discretize this in time to yield some particle system in the space Rd. So yn plus 1 would be yn minus step size tau times the gradient of the potential evaluated at y plus some normally distributed random vector. I'm instead going to focus on particle methods, which are used in variational inference a lot, which take a different approach by defining some sort of discrepancy f, which will be discrepancy to the target measure pi, like the KL divergence, for example, or different other divergences, and then minimize this divergence by running the densities along a Wasserstein gradient flow. So instead, our continuous time equation will be the time derivative of a density rho, which is the distribution of some particles, should be equal to minus the gradient in a suitable sense of our discrepancy f evaluated at rho t. We can then, because this is just a deterministic system, right? There's no Brownian motion involved, discretize this explicitly in time again and get this gradient descent type update. Rho n plus 1 will be rho n minus some step size times this kind of gradient of f evaluated at rho n. And one class of methods that falls into this category is Stein variational gradient descent in a certain sense. And as we've seen, as I mentioned, like a month ago, Stein variational gradient descent has this kernel k, which is a symmetric, positive, definite, and in our case, differentiable function from Rd times Rd to R, which somehow tells us how close two points are. And the update reads like this. We have n particles, xi, from I to n, and then the small n plus 1 iteration, we update the particle by subtracting this term. So we have, again, the step size tau, and then we have this sum, which is the attraction term, which has this gradient of the potential again, which kind of makes the particles move towards the target, and the repulsion term, which involves the derivative of the kernel and makes sure the particles don't just all collapse into the mean of the target distribution, but instead spread out evenly in a certain sense. Now, this looks nice, but the question now is where does this come from? What's the underlying concept beneath it? And this is what Liu and Wang conceptualized 10 years ago, basically. Supposing these particles, xi should be a subindex, follow some distribution rho, then we can write this update as these particles being mapped by this map ti to the next iteration. And this map ti is the identity plus step size times some direction phi I. And the phi I is chosen in a very particular way. Namely, it maximizes this expression where we take the partial derivative with respect to this step size, so how much we go into the direction phi I at eta equal to 0, of the KL divergence of basically our current distribution rho mapped, basically perturbed a bit into this direction against the target measure pi. So we have this kind of directional derivative of our objective, which turns out to be the KL divergence to our target measure pi. And we can calculate this partial derivatives, and it takes the form of some expectation against the current density of the particles rho. And if we now replace rho by the sample average of these n particles, we can solve this maximization problem explicitly because we're in a reproducing kernel Hilbert space and get exactly this update. So what we've seen is that Stein variational gradient descent, SVGD, is a gradient descent of this objective, KL divergence with target pi, with respect to a certain kind of geometry induced by this kernel K in the continuous sense, and then to get to something implementable, we replace this current density by a sample average. Yeah, so to maybe circle back to something like more simple, if we were just in Euclidean case and not a functional on densities, the gradient, in this case normalized, would also be the maximizer of this partial derivative at some point in the direction v, when we maximize over all directions. And this is exactly the same here, just that in this above formula for the SVGD, we're in the space of densities, but the idea is the same. So this contribution shows SVGD is just some type of gradient descent with respect to a different geometry on the space of densities. And having this choice of kernel opens up a lot of possibilities. In our work, we first focused on the Gaussian kernel, which is very well known, very smooth, and the bilinear kernel, which has this matrix A as a parameter, which we can choose to improve convergence. And they are basically two representatives of like two different camps of kernels. We have radial kernels, which depend on the difference of the arguments, and non-radial kernels. Yeah, and as this graphic shows, there are a lot of different kernels one could also consider with varying degrees of smoothness, but we only focused on these two at the beginning. So what I'm going to tell you now is about accelerating gradient descent, Nesterov style, which is a concept which will then also apply to the SVGD. And the general principle, I'm sure you know, is if we have some minimizer x star of some convex differentiable function f with Lipschitz gradient, then one way to find this minimizer is to do gradient descent with a step size depending on the Lipschitz constant, and then we have linear convergence. So we know the function values theta k in a monotone fashion, and we have linear convergence rate O of 1 over n. And the idea of Nesterov in the 70s or 80s was to add this momentum step to this gradient descent update to then get quadratic convergence, so one order better, which is quite significant. And so instead of just doing the gradient descent update as we had here, he plugs in a different point yn into the gradient end here, which is like some kind of extrapolation between the current iterate and the difference to the iterate before. So the amount we move from one step to another also has an influence on the next step. So we have this kind of look forward property where the steps are not basically independent of each other, but if we made a big step, big leap in the last step, this influences the step we're going to make next. This, however, introduces these damping parameters, which have to be chosen in some fashion. And the classical choice is if this function is merely convex, to choose this n-1 over n plus 2, and a constant if we even have strong convexity. Now let's get some intuition how this works in practice. I hope you can see this second screen, this animation now as well. So if we do normal gradient descent, so no momentum, no alpha, which is called beta here, you can see here we have a function R2 to R with these level lines, and gradient descent always moves orthogonally to these level lines, so we have this oscillatory behavior and very slow convergence. If we take these 500 steps, I think it is, our solution is quite far from the optimum. And if we increase the step size, we get closer to the solution. However, if we choose our step size too large, we have this jumping around behavior and we don't recover the optimum at all. So let's go back to a smaller step size and crank up the momentum and see what happens. So we can see this oscillatory behavior at the beginning gets smaller and our solution moves closer to the optimum. So if we increase it to, let's see, this looks like a good parameter, like 0.88, we recover the optimum very well. And you can see this, our iterates move around, not in a smooth fashion, but kind of wriggly, but they don't move orthogonally to the level lines anymore, which in this case is something good, because otherwise we would converge very slow. So adding this momentum is helpful in this case, but we can also see that if we choose the momentum too large, then again, we fail at recovering the optimum. So what have we seen? Well, first of all, gradient descent gives a monotone decrease in functional values, while the accelerate method might not. And we've also seen too high momentum makes our trajectory overshoot the minimum and oscillate, while too small momentum gives us too slow convergence, not enough exploration. So we can also see this very nicely from the graphic on the right here, where the y-axis is the difference of the functional value to the optimal value, which for purple gradient descent, we have relatively slow convergence and not very good like optimal value. For the accelerated one, we get these ripples and non-monotone behavior, but faster convergence. And if we now do the adaptive restart, which means setting the momentum back to 0 when it gets too big, we get even better convergence. So this restarting technique, which is not that well explored theoretical yet, but there are some results in these two papers below. They posit to say, well, if the momentum gets too large, set it to 0. So basically pretend you're at the beginning of the algorithm again. When a certain condition is fulfilled, and there are multiple ideas. One is a function restart. The simplest idea, if our functional values get bigger, then reset because we want to decrease. However, in sampling, this is not feasible because we can't evaluate the objective directly, right? We have some particles who are pushing around, and our KL divergence from the particles to the target distribution will always be infinite because one measure is discrete and one is continuous. Something different we can do is a gradient restart. So here we look at the angle of our gradient and the difference of the previous iterates. And if basically our search direction moves, it won't be orthogonal to level lines, but if it moves too far away, too much in the bad direction, this will be negative. And then we also restart the momentum and say, okay, this is not a good idea. Let's basically start over again. Take as new starting point the last point we had, but reset the momentum to 0. And even more easy to implement the speed restart, which says, well, if the progress we're making per iteration decreased, then also set the momentum to 0, because maybe there's a different, better direction to be found. So now we've covered accelerated gradient descent and also how we can improve it in practice by using this restarting technique. Now we're gonna apply this Nesterov idea of accelerating gradient descent to the Stein variational gradient descent I've showed you before. So if we look at this update formula I showed you here, you hopefully agree it's not immediately clear how the accelerated version of this would look like, right? And the key is that this is just a discretization of these continuous dynamics on the density space. So what we'll develop is we're going to look at the space of densities more in more detail, and then derive an alternative formulation of Stein variational gradient descent, from which it is immediately clear how to apply this Nesterov idea. So let's look at this manifold, and to make the analysis doable, we're going to look at only these densities on some domain omega, which has nice boundary conditions, which are positive and integrate to 1 and are smooth, so C infinity. What's the reason for this? Well, John Lafferty, who like 40 years before he ever did any machine learning, showed that this space actually has a manifold-like structure. So under technical assumptions on the space omega, this forms an infinite-dimensional smooth Fréchet manifold, which is a certain generalization of Riemannian manifolds to infinite dimensions. If one swallows this, one has some kind of tangent space, which in this case will be smooth functions with mean 0. And again, this is technical. In these infinite dimensional Fréchet manifolds, you can have multiple definitions of tangent space, and we pick a specific one. And we then also have a cotangent space, which we identify with smooth functions modulo some constant. And because Fréchet manifolds are complicated, in this case, we don't even have this duality that the dual of the tangent space is the cotangent space. But with these definitions, we can make it work. I'm just going to remark that basically underneath everything, there's a lot of complicated theory going on. And once we've defined this kind of manifold of smooth functions with tangent and cotangent space, we can also define a kind of Riemannian metric. So for each point rho in this manifold of densities, we can define an operator G rho from the tangent space to the cotangent space. And the collection of all of these will be our metric tensor, which then defines basically the angle between two densities. And in the Riemannian case, in the finite dimensional case, would just be lowering of indices, right? So this is the Riemannian type geometry of this manifold of smooth probability densities. And now that we have this kind of manifold structure, we can think about gradient flows in a density manifold. So we have an objective function, E, on this density manifold, like the KL divergence. And we want to define a gradient flow with respect to this functional. And the helpful thing is that, well, all these smooth functions will also be L2 functions, but L2 has this nice scalar product. So we use this linear ambient space to first define this functional derivative. So we could just take, well, we say this first functional derivative of E at rho in direction phi is just like you would define this directional derivative. And then we define the gradient in this manifold of densities to be, well, this inverse metric tensor applied to this linear derivative. So a gradient flow would then be, well, the time derivative of this density is minus this gradient in the manifold of densities of the objective functional. So this is the linear derivative basically, and this metric tensor then deforms it in such a way that it respects the geometry of this manifold. This is basically like a covector, and then the inverse metric tensor is applied to it to make this the manifold kind of gradient flow of this functional. So now we can look at different metrics on the space of probability densities and how the gradient flows will look like. Two examples. First, Wasserstein, we all know, and we have from the paper by Otto also, right? This is what often is cited. We define it to be the inverse metric tensor of some cotangent vector phi will be minus divergence of rho times grad phi. And now we can see this makes sense if our functional is, again, the KL divergence to our measure pi. And we now plug this definition in. The gradient flow time derivative is minus the inverse metric tensor applied to the functional derivative. Well, the functional derivative of the KL divergence is log rho plus potential v. And so if we plug this into here, we take the gradient of the functional derivative, so the gradient of log rho t and gradient of v, and then the minuses cancel, so we get divergence of rho t times this term. And now if we apply some calculation rules, we get the Laplacian of rho t plus divergence of rho t nabla phi v. And so, for example, if the potential would be 0, this would be the heat equation, and this is the result we all know from Wasserstein gradient flows after KL divergence. Now let's see the metric induced by the kernel, the Stein metric. So here we kind of kernelize this operator. So we still have minus the divergence of rho times something, but we don't just have nabla phi here, but we have this convolution type integral where we integrate nabla phi against the kernel and then again integrate against the density. So we kind of move this covector nabla phi into the reproducing kernel Hilbert space by integrating against this kernel. And then we can make this a similar computation. So again, we get the gradient of the functional derivative. This nabla phi will be grad log rho t plus nabla v. But now we integrate it against the kernel, which we didn't have here. Here we just have multiplication. Here we have this integral. And now what we can do is shift this derivative onto the kernel. So, excuse me, there's k times nabla v is preserved, but the second term, here we have rho t times nabla grad v, which is just grad rho t, and integration by parts now allows us to shift this derivative onto the kernel, and we're left with, inside here, an integral, or an expectation basically, with respect to rho t. So if we now replace rho t by some sample average, this is again a tractable formulation. And this is the key idea, why SVGD works so well. We can do this integration by parts and shift the derivative on the kernel. In the Wasserstein case, we don't have a kernel and we can't shift the derivative somewhere. But here we have, and so if our kernel is differentiable, we can do this. So this is now gradient flow on densities. And now let's see how accelerated gradient flow on densities will look like. And here, an important contribution is due to Tandes, who showed with coworkers that if we take the accelerated gradient descent of Nesterov that I explained a few minutes ago, and basically take the continuous time limit in a certain sense, one gets that the continuous trajectory that this accelerated gradient descent traces when you let the step size go to 0 is the solution of a second order differential equation. So for gradient flow, we get first order differential equation. the accelerated one, we get a second order ODE, which takes this form. So we have the second time derivative plus this damping, which again, depending on the convexity, takes one of these forms, times the time derivative of the particle, plus the gradient should be 0. And now the idea in an earlier paper by Wuchen is that, well, we can rewrite the second order ODE into a system of two first order ODEs, right? By saying, well, x here in this case represents position and the derivative would be the momentum. And so if we write then out this second order ODE into two first order ODEs, which are coupled, we can get this form. We define this Hamiltonian, which is kind of kinetic energy, well, the squared momentum, plus the potential energy given by the function to minimize. And then the gradients with respect to these two variables of the Hamiltonian are very simple. They are p and grad f. And then if one plugs this in here, one gets exactly this formulation back. But this structure is very well known. It's a damped Hamiltonian flow, and this generalizes very nice to the density manifold. So we've now seen in the normal Euclidean setting, we can rewrite accelerated gradient descent in the continuous time limit as this Hamiltonian flow. And this formulation is easily generalized to the density manifold in the following way. Basically, we just have to define what the Hamiltonian should be in the non-Euclidean setting, and then we can just copy this formula, and we get accelerated gradient flow in the manifold of densities. And so what do we do? Here we have the Hamiltonian is kinetic energy plus potential energy. And if we go to densities, well, the potential energy should still be the function we're trying to minimize. The kinetic energy, well, that's the squared Euclidean norm. If we're in if we would be in a Riemannian manifold, this would instead be this quadratic form, which is something like x transposed ax, where a basically gives the curvature of the manifold. So here, the metric tensor again enters, which describes how the manifold is curved and depends on the metric we choose on these densities. And this again is exactly this kinetic energy term. And so now the rho are the position variables, the densities, and the phi's will be the momentum variables. And now we can again calculate the derivatives of the Hamiltonian and write down exactly the formula I had before here in the space of densities. So we now have the time derivative of rho should be the inverse metric tensor applied to the momentum, and the momentum should satisfy this equation. This E here should not be here. So the time derivative of the momentum also has an equation it has to fulfill. And here we have again the functional derivative. So if we then plug in our definition of the inverse metric tensor for the Stein metric, we get this formula, which now looks complicated, that's true. But we'll see that in a second that it's very nice to do in particles as well, and then yields a very straightforward to implement particle algorithm for sampling for densities. So just a quick recap, what did we do? We looked at Stein variational gradient descent, which is very attractive, saw that it is the continuous time formulation of a gradient flow in the space of densities. We also looked at how one can accelerate gradient descent in the Euclidean format and how then we can use the same idea to accelerate gradient flows in the density of the manifold of densities, and now arrived in continuous time and space at accelerated Stein variational gradient flow. Now the question is, how can we discretize this to again get a nice particle algorithm like we did for Stein variational gradient descent? And the straightforward idea would be, well, we replace the densities by like empirical estimates, just empirical measure, direct measures at n particles, xj. And also we have to model the accelerations now that we're in this scheme where we have these position and acceleration or momentum variables. And then we would forward discretize in time as the simplest possible idea. Implicit schemes seem difficult. They're also conformal symplectic schemes, but now we're just going to focus on forward Euler. And in their earlier paper by Wuchen and one of his students, they use the following scheme. So they set MT, now in my notation, to be this gradient of the momentum at the positions. And then they get this discrete scheme. So they have an update equation for the positions of the particles with this sum over the kernel, which looks similar to what we had for Stein variational gradient descent, and the update equation for these acceleration parameters, where we have the damping, and we have this kind of repulsion term again, where we have the derivative of the kernel. However, when we discretize the functional derivative, right? Remember here we have the functional derivative of our KL divergence. They get the derivative of the potential plus some psi, and these psi are kernel density estimates of the score functions. So in each step, they have to estimate the score to get these terms so they can update their acceleration parameters. However, as we know, in high dimensions, kernel density estimation does not work very well, and it's very sensitive to how one chooses the kernel width. So in their paper, they have some new like Brownian motion method to do it, but in general, this can be suboptimal. So what we did is come up with a different way of discretizing the system, which does not need score estimation. So the idea was to, instead of using the second variable xt, we dot t, which we can express by this integral formulation with the kernel k, which again, as you can see here, is an expectation with respect to rho t. So if rho t is approximated by samples, this just becomes a sum, a kernel sum. And the necessary computation, which now facilitates this, and again uses this principle of SVGD that we use integration by parts to shift derivatives from the density to the kernel, we now get in the accelerated scheme that using these two variables x and y, instead of the variables they used in the earlier paper, we can also write down an interacting particle system for that discretizes the accelerated Stein variational flow. So xt dot is yt, because that's how we defined it, and we can now calculate the update equation for yt, which model our momentum parameters with this damping term, some well, basically an attractive term again, which moves the particles towards the target, and some repulsion term. Notice again here, this is just an expectation with respect to rho t, which is what we want for discretizing. And then additionally, this, well, interacting term, which is an like a double integral, but again, twice an expectation. It has this kind of interacting kernel term where we have some like these double terms, always a kernel and a kernel derivative, and they tell us how the particles should interact. And if we now discretize this in time, we get the algorithm which we can use for sampling, which models the accelerated Stein variational gradient descent. So in this continuous formulation, we replace again these rho t by sample averages, as I mentioned, and discretize forward in time. And then so what we get is the following. Recall the first equation was just x dot is yt. So in discrete time, this will be xk plus 1 is xk plus step size times yk. And then we have to somehow discretize the second equation. And so what we do is we first construct a kernel matrix, of course, because we have lots of kernel terms here in these in this formula, and basically extract these momentums from our yks from the previous iteration. So recall that here we defined y to be this integral of k times this nabla phi t integrated against the position of the particles. And if we now replace these positions by the sample average, this is a linear system we can solve depending on the kernel matrix. So here we basically invert with a kind of regularization this kernel matrix to infer these accelerations. We can then use restart methods to improve convergence. I didn't write the formulas here, but they are exactly the same principle like I've shown in the Euclidean case, and then use this update formula for the y variable. So for as you've seen on the previous slide, this is quite a mouthful, this formula, but for the bilinear kernel, it looks doable. So we have, again, damping, potential term, and then this term here, which depends on this matrix A we choose in the bilinear kernel. And for the Gaussian kernel, we also have a similar equation. If you look at the second one here, we have the damping, we have the potential term, and then here we have some kind of Laplacian term with this auxiliary matrix W, which is defined by some kernel interaction terms. And this now gives us a fully discrete in time and space discretization of this accelerated Stein variational gradient flow. Now let's look at some examples. So for the generalized bilinear kernel, which I showed at the beginning, which is just like x transpose y, and maybe some matrix in the middle to improve convergence, it is known that Stein variational gradient descent starting from a Gaussian with Gaussian target stays Gaussian. And this is also what we observed. And here in these plots, let me zoom in perhaps a bit, they work as follows. The particles start in the blue positions and move towards the red particles. And the color indicates at which point they are where. And the black lines are the isolines of the target density. So you can see here we started with a Gaussian that's basically in this direction. And the target is a Gaussian in exactly 90 degrees rotated. And so one can see here that on the very left is accelerated Stein variational gradient descent. And on one further right is just normal Stein variational gradient descent. And the trajectories look similar. However, one can see, I hope one can see this well, that in the accelerated one, we have kind of some overshoot. The particles don't just move in a direct fashion like they do here, but here they basically move a bit above and then they go back, which is very reminiscent of this momentum methods, like I showed at the beginning, that one has this oscillatory ripple behavior. And then we also compared with diffusion-based methods, so two ones, Mahler and underdamped Langevin dynamics. One is first order and one is second order. And one can notice two things. Excuse me. First, because these diffusion-based methods add randomness in every step, there's a lot more variance going on. The particles move a lot more, especially for the underdamped Langevin dynamics. And they also don't necessarily have such an orderly structure, but this will be a bit clearer even in the other plots. And we can also, at each iteration, approximate at least our loss function and plot it. And so what we can see here is, for a sanity check, accelerated Stein variational gradient descent, so ASVG, blue is always faster than orange, non-accelerated. And for a different kernel parameter, green is faster than red. And we can also see that they are faster than the randomized method. So I also have some ULA here, some unadjusted Langevin, underdamped Langevin, and the Mahler. And for non-Gaussian targets and the Gaussian kernel, we even have some more clear advantages. So for the first target here in the first row, again, accelerated, non-accelerated, Mahler, and underdamped. We can see that, first of all, for this non-Lipschitz potential, SVGD works very well. The particles move basically very directly to the target. They are arranged very neatly at these level lines. they don't basically move to the other side and then have to move back. They have very good path. And other algorithms like the Mahler, which has this acceptance step, struggle with the non-Lipschitzness of the target. So many particles like get rejected and don't move at all. And this is not a problem for our algorithm. Secondly, this momentum we built into our method can help improve exploration drastically. So here we can see we have this double bananas target and we initialize the particles just on one side. And for example, for SVGD, here in the middle, we can see that the particles just explore one mode, and the same for the Mahler. However, if we choose a second order method like our accelerated SVGD, we can achieve something similar to the underdamped Langevin dynamics, where the momentum makes the particles also explore the different mode. So we have this advantage, but we have a deterministic system with no randomness and no bias. And what we can also see is that for this very anisotropic target here, the Gaussian target, which looks like this, again, for accelerated SVGD, the particles move very clear directions, arrange very neatly, and again, accelerated is faster than non-accelerated. But the other methods struggle a lot. And the reason for this is that our particle system is an interacting particle system, while the fusion based methods are non-interacting. So what happens here is that the particles basically overshoot in one direction, because you can see due to this being non-isotropic, one basically has to choose very different step sizes into the horizontal and the vertical direction. But because the particles don't interact, this impacts them severely, and they can only basically do a trade-off and move too much in one direction or too little or too much in the other direction. While in our case, due to the interacting nature, the particles influencing the other particles and making them go to the target, we don't have this behavior at all. And also for these plots, we can see in the functional value that our methods work really well. For example, here the first plot is this example from the top row, and one can see, for example, that here Mahler does very badly because most of the particles don't move, while our method is competitive, and accelerated SVGD is much faster than SVGD. And the same can be said for the other two plots. Again, blue is our method, accelerated SVGD converges much faster. And in the second example, it finds the second mode, so it goes down much faster. And the other methods, they only find one mode, so their asymptotic functional value is much higher. Okay, now let's cover some open questions before I end. So things that are still to do and are also very much in progress already are finding the best kernel parameters. So we now have this accelerated scheme, which is kind of optimal because Nesterov schemes are optimal among first order methods, but we have these kernel parameters we can play with. And the question is, can we somehow infer from our target distribution some information to choose our kernel in a way that convergence is improved? So how do we find the matrix A in the bilinear kernel or the variance of the Gaussian? Similarly, what's the best damping? Can we also, like in the Euclidean case, like in this paper by Candes, find optimal damping parameters, or at least approximate best damping parameters, taking into account that we're now on this manifold of densities, which has some kind of curvature depending on the metric we use. Can we do better discretizations? So as I showed you, we have this Hamiltonian system, which has like very physical interpretation, and lots of physicists looked into how to discretize these dynamics in time to preserve important quantities along the flow, like dissipation of certain Lyapunov functionals. Can this be applied as well? There are some troubles, but I think this is quite promising. See if we have some bias in the algorithm, of it can be removed with some kind of acceptance step as well. And something that also was applied to SVGD is to improve convergence in higher dimensions, use some annealing strategy to like modulate the impact of one of the terms. Remember, we have this attractive and the repulsive term. And in order to mitigate variance collapse, they use some annealing strategy, which also would benefit our algorithm, I think. And with this, I want to end. Thank you for your attention, and I'm happy to take any questions. And I've put the links to the paper and the code here below. There are some issues with Stein variational gradient descent in high dimensions, and I'm not yet sure how well we can address if our accelerated scheme suffers from the same has the same problems. Our toy examples are in very low dimensions now, and I'm currently working on implementing this in higher dimensions and like this like a Bayesian neural network framework. But to mitigate disadvantages of SVGD in high dimensions, there has been a lot of like progress, and I'm pretty sure that these strategies, like the annealing one I mentioned, can also be then applied to our method. So we should be, I think, from my intuition, should benefit from the same improvements as SVGD, just have the advantage that our algorithm is faster because it has this acceleration scheme built in. But that's a very good question, yeah. It's very important. Don't know yet. So yeah, I'm not sure. We're still figuring out a lot of theoretical details, which will like inform then like a second version of the paper. But I don't know if it's gonna be what the order will be. But we expect obviously the accelerated one to behave similarly to how it's in the Euclidean case, which then would be a better asymptotic dependence. Yeah, so in the paper by Wuchen from a few years back, they do it for the Wasserstein case. And that is possible to just, as you mentioned, design a Lyapunov functional, and then you can prove entropy decrease and get a convergence bound. For the accelerated SVGD, it depends a lot on the kernel, obviously, how much regularity you get on the densities to prove such a result. And one thing that I think would be necessary to get a good proof is to explicitly use this kind of regularization we used at the begin in this algorithm. So I mentioned one has to basically invert the kernel matrix in every step, which can become ill-conditioned. And so we add this epsilon times identity to this matrix to make it well-conditioned. And this is exactly basically adding to our Stein metric epsilon times the Wasserstein metric. So we kind of have a bit of a mixed metric where we don't do pure Stein metric descent, but add a bit of Wasserstein. And I think that adding this Wasserstein term, which is like an L2 regularization basically in density space, should make this possible to prove convergence. But as of now, we don't have a rigorous result in that direction. A good question. That's on the to-do list for sure. Well, thank you very much. Thanks for the invitation again.